All right, so let's start on page 53. We're on section 3.6, rational functions. And basically the objective here is to first analyze rational functions and then how to sketch a graph of a rational function. Okay, so everything we've looked at so far in this chapter 3 has been polynomial functions, p of x, where p of x is a sum of terms. You're adding the terms together. The domain is always all real numbers, negative infinity, comma infinity, and the graph is smooth and continuous. So now we're looking at something completely different, rational functions, which are defined as the quotient of two polynomials. Okay, so quotient, of course, means division. Okay, so in other words, we're taking one polynomial, n of x, n for numerator, divided by another polynomial, d of x, d for denominator. So that is what makes a rational function, okay? And it's different because the domain is not all real numbers. It consists of all real numbers for which the denominator is not equal to 0. Of course, you cannot have 0, you can't divide by 0. So therefore, they're quite different from polynomial functions because the domain is restricted by the denominator. Okay, again, you cannot have the denominator equal to 0. Because of this, the graph is still going to be smooth, but often not continuous. All right, so we've already looked at this back in chapter 2. The parent rational function is just 1 over x. And we actually already plotted this. And we already know that the domain is basically x cannot equal 0. Okay, because you can't have, 1 divided by 0. So in other words, negative infinity, comma, 0, paren, union with paren, 0, comma, infinity. Okay, that's the domain of the parent rational function. All right, so let's look at some of the points that we used when we plotted this back in chapter 2. These are the values I gave you. These are the values you guys calculated and used to plot. So for example, at x equals -4, the output is -1 over 4 because it's the reciprocal, just take 1 over it. So that's this point right here. -2, -1/2 is right here. -1, -1, -1/2, -2, -1/4, -4. Okay, so if we add in a couple more points on this half of the graph, say if we did x is -1 over 10, then the output, the reciprocal of that, would be -10. So I'm getting close to 0 here. I would be way down here somewhere on the graph. I can't actually add it in, but it would be somewhere like here. Or if we even said, well, what happens if x is -1 over 100? Well, the reciprocal of that would be -100. Okay. So what's happening on the graph now is I'm extremely close to 0 and I'm way, way down here on the graph. Okay. So in general, as x is approaching 0 from the negative side, in other words, as I'm moving this way towards 0 from the negative or the left side, f of x is decreasing without bound. Or in other words, it is approaching negative infinity. Okay? So in symbols, we would write this the following. We would say as x is approaching 0 from the negative side. So that's actually a little superscript negative symbol. F of x is approaching negative infinity. All right, so again, as I'm coming this way, f of x is shooting down to negative infinity. So we can do exactly the same thing on the positive side. Again, these are the points I already gave you. You guys calculated, you plotted them. If x is positive 1/4, y is the reciprocal of that, which is positive 4. That's this point right here. 1/2, 2, that's right here. 1 and 1, 2 and 1/2, 4 and 1/4. So in this case, if we come up here and move closer to 0, if x is positive 1/10, y is the reciprocal of that, which is 10. So now I'm like here, and then my point would be way up here somewhere. It's going to go off the top of the graph. If I get even closer to 0, okay, positive 1/100, y is the reciprocal of that, which is positive 100. Okay. So in this case, as x is approaching 0 from the positive, the right side, so this time we're coming closer to 0 in this direction, okay, what we see is that f of x is getting very large, okay? It is increasing without bound, or it is approaching positive infinity. So in symbols, we would write as x approaches 0 from the positive side. So again, that's a superscript, a little plus sign. F of x is approaching infinity. Okay. So the point is, the function will never touch or cross the line x equals 0. Okay? It can't because the function is not defined there. So that is what makes, sorry, that's supposed to be a straight line. That is what makes the line x equals 0, in other words, the y-axis, a vertical asymptote. All right. Okay, I'm going to dump all this and move on to the next page. So here from the book is the actual definition of a vertical asymptote. The line with equation x equals a, so x equals a constant, some number, is a vertical asymptote of a function f if the absolute value of f of x approaches infinity, as x approaches a from either the positive side or the negative side. Now what this means is basically it's the same as saying either f of x approaches infinity or f of x approaches negative infinity. They're just putting it in absolute value bars. Okay. And here's a good figure from the book kind of showing the various behaviors as a graph approaches a vertical asymptote. So in all cases here, you can see they've got A indicated. The dotted blue line indicates the vertical asymptote. And again, here is x approaching A from the negative side. Okay, it's coming up from the negative side. Here is x approaching A from the positive side. And there's all these various scenarios. Maybe in both cases it shoots up to positive infinity. Maybe in both cases it shoots down to negative infinity. Or it can also have the opposite behavior. All right, I'm going to dump this and move on to the next page. Oops. Okay, so let's talk now about how do we actually locate these vertical asymptotes on the graph. So again, we've got a rational function n of x divided by d of x, where n of x and d of x do not have a common factor, and we'll talk about that specifically, and a, the value of x equals a, is a real zero of the denominator, then the line with the equation x equals a is a vertical asymptote of the graph. Okay, so the key point here is that the vertical asymptotes will occur at the zeros of the denominator, as long as the rational function is in lowest terms. Okay, and what that means is that the numerator and the denominator do not have any common factors. Okay, they do not have any common factors. So let me show you an example of what that means. You just scooch down here a little. Okay, so here is a rational function, x minus 3 over x squared minus 4x minus 5. So what we can do is we can factor that denominator. Okay, so if I factor the denominator, then we have f of x equals, all right, so nothing changes in the numerator, it's still just x minus 3 over, and then this would factor as x minus 5 times x plus 1. So you can see there are no common factors. There's only one factor in the numerator, and it doesn't match either of the factors in the denominator. Okay, so there's nothing I can cancel. There's no common factors. That means that this rational function is in lowest terms. Therefore, the vertical asymptotes will occur at the zeros of the denominator. So in other words, at x equals 5, or at x equals negative 1. Okay, and if you look at the graph, and again, I'm not going to be able to draw a really great straight line as promised. This is a horrible line, but this would be the vertical asymptote at x equals negative 1. And over here, if I could draw a straight line, it would indicate that there is a vertical asymptote at x equals 5. All right, I'm going to dump this and go on to the next page. All right, so a slightly different example. So we have a different rational function now. So again, if we start by factoring the denominator, x squared plus 8x plus 15 factors as x plus 5 times x plus 3. But in this case, it's a little different because we can actually also factor the numerator. Okay, so let me just write this up here so I don't have to recopy it. So now I'm going to show you the fully factored form where I also factored the numerator, which factors as x plus 5 times x minus 2. All right, so that is the function in fully factored form. And as you can see in this case, there is a common factor, okay? So we can actually, cancel those factors. So that gives us the function x minus 2 over x plus 3. And we would say now that it is in lowest terms, okay? So because of that, the graph is only going to have a vertical asymptote at x equals -3. All right, so that is where the vertical asymptote is going to be. Okay. However, when we want to write the domain of the function, we have to look back at the original function, not the canceled form, not the lowest terms form. We have to look at the original function, which had, these two factors in the denominator. So in other words, for the domain, we have to say, well, x cannot equal -5, and it can also not equal -3. Okay. So if we were going to write the domain in interval form, we would write, and I'm just going to say this, I'm not going to write it out, -∞, -5, paren, union with paren, -5, -3, paren, union with paren, -3, infinity. So in other words, we're just excluding these two values. Okay. So when you plot this, okay, I'm going to dump this stuff and then scooch the page up a little. When you plot this, the graph will look like this. Okay, so we can see that it has, as we said above, the vertical asymptote at x equals -3, so that's here. So here's the vertical asymptote. Okay. But it also is not defined at x equals -5. Okay. And the graphing utility is not smart enough to know this. Even though, as you can see over here, I've typed in the original function, not the canceled function in lowest terms. So it should know that there's no function defined at x equals -5, but I don't know of any graphing utility that will actually do this. So what we have to do is we have to go back and put an open circle there at x equals -5 to indicate that there is in fact no function value there. Okay, so what this is called, this particular point, it is called a removable, I'll go ahead and write this out, even though it takes me a little while to write with this. How do you spell that? No E, okay? It is a removable discontinuity. Okay, discontinuity. In other words, the graph is actually discontinuous at that point. Okay, and again, this occurs at x equals -5. All right. And let me also just go ahead, let me pull Desmos over real quick. All right, I'm going to have to erase that stuff. You guys got all that? I'm going to erase it. Let me just type in the original function, which was x squared plus 3x minus 10 divided by x squared plus 8x plus 15. All right, so that's basically the same graph we were just looking at. I just want to show you guys a couple more things you can do in Desmos. You might want to use this on the homework assignment 6. If I want, I can add in the vertical asymptote, which was at x equals -3. So I'm just going to type in x equals -3, gives me a line. If you want to change that, say, to a dotted or dashed line, if you left click right here, and then I can change the style, like there, okay? Another thing we can do is we can actually add in that removable discontinuity. Okay, it would be at the point, if you look back up on your page, when we canceled the common factor, the function was reduced to x minus 2 over x plus 3. Now we know that the discontinuity occurs at a value of x equals -5. So if I plug -5 into that, I would have -5 minus 2 over -5 plus 3, which equals -7 over -2, which equals 7/2, which is the same as 3.5. So the discontinuity point, and you can just also plot points in Desmos, is equal to the point -5, 3.5. All right, so you can see the point just appeared on the plot there. But what I really want is for that to be an open point. So again, just left mouse click here, change the style to an open point like that. Okay. If you want, you can change the color. I'm going to make it black. And if you want, you can add a label. It'll label it with the coordinates. Okay. Okay, let's move on to the next page, page 58, horizontal asymptotes. So again, let's go back and look one more time at the parent function, f of x equals 1 over x. And this time we are looking at the left and right end behavior of the graph. So in other words, as x gets very large or as x gets very negative, what is the function value doing? What is y doing? Okay. And what you can see is that it appears that the graph, it's going to continue out this way. It's going to get very close to the x-axis but never touch it. Same thing here. It's going to continue on this way. It's going to get close to the x-axis, but it's never going to touch it. So in other words, the left and right end behavior of the graph is the same. We can see that the function value, f of x, or same as y, is approaching 0, okay, as x is approaching either plus or negative infinity. Okay. So this indicates that the line y equals 0, in other words, the x-axis, is a horizontal asymptote of this graph. Okay. So right here is the definition of the horizontal asymptote. The line with the equation y equals k, so where k is just a constant, a number, is a horizontal asymptote of the graph if f of x approaches k as x gets very positive or as x gets very negative. Okay. All right, so horizontal asymptotes are a little different than vertical asymptotes. For one thing, the graph can touch or cross a horizontal asymptote. Whereas, as we've already seen, the graph can never touch or cross a vertical asymptote because the function simply is not defined there. Also, a difference is that a rational function has at most one horizontal asymptote, versus we've already seen that it can have more than one vertical asymptote. All right, so how do we find the horizontal asymptotes? Well, you have to understand this statement. As x approaches plus or negative infinity, in other words, as it gets very, very large or very, very negative, the behavior of a rational function is determined by the ratio of the leading terms of its numerator and denominator. Okay, so again, the ratio of its leading terms. So that means this. These are the leading terms of the numerator and the denominator. So this over this is the ratio of the leading terms. And also what I want to point out to you is you can see here the numerator is of degree n, whatever that is. The denominator is of degree m. So what we're going to end up looking at in the next few cases is how do those degrees compare, the degree of the numerator to the degree of the denominator. All right. So we're going to look at three specific cases. Let's start with case 1. And specifically here, the degree of the numerator is less than the degree of the denominator. Okay. And again, what we want to look at is the ratio of the leading terms. So that would be this. So in the numerator, we have 3x, same as 3x to the 1. So in other words, n is 1. And then in the denominator, we have an x squared. So in other words, m, the degree of the denominator, is 2. So yeah, 1 is less than 2. Okay. Now, if we just look at the graph of this function, 3x plus 4 over x squared plus 1, this is what it looks like. Okay. And just by inspection, it looks as if when x gets very positive or as x gets very negative, it looks like the graph is approaching the line y equals 0. Okay, so in other words, the end behavior is f of x approaches 0 as x approaches plus or minus infinity. All right, so we can kind of summarize the results below. For a rational function, when the degree of the numerator is less than the degree of the denominator, then the line y equals 0, and again, that's the same as the x-axis, is the horizontal asymptote. And that will always be the case when n is less than m. All right, let me move on to the next page. Case 2. So in this case, the degree of the numerator is equal to the degree of the denominator. Again, if we look at the leading terms, we see the degree of the numerator is 2. We see that the degree of the denominator is also 2 because they're both x squared. Okay. And by looking at the graph, just by inspection, where does it appear that the horizontal asymptote is as x is getting very large or very negative? Okay. If you look at that carefully, yeah, you should be able to see it looks like it's right here at the line y equals 4. Okay, it looks like that is what the graph is doing, okay? So that would be the end behavior. So in this case, f of x is approaching 4 as x is approaching plus or minus infinity. All right, and in fact, that happens to be the same as the ratio of the leading coefficients right here. X squared is really the same as 1x squared. And what we've got here is 4 over 1. So we can summarize that down here. If f is a rational function, when the degree of the numerator is equal to the degree of the denominator, then the line y equals a sub n divided by b sub m, or in other words, the coefficient of the leading term divided by the coefficient of the leading term, is going to be the horizontal asymptote. So again, in this case, that was a 4 divided by 1. All right, let me move on to the next page, which is case 3. Okay, so in this case, the degree of the numerator is greater than the degree of the denominator. So here are the leading terms. All right, so the degree of the numerator is 3. The degree of the denominator is 1. 3 is greater than 1. Okay. And here's a graph of the function. And again, by inspection, what does it look like is happening? As x gets very positive, the function value is just shooting up. It's unbounded. It's approaching infinity. As x gets very negative, we see the same thing. The function value is shooting up. It's unbounded. It's going to infinity. Okay. So in this case, the end behavior is that f of x is approaching infinity as x approaches plus or minus infinity. So in this case, there is no horizontal asymptote. Okay, so down here we've got a rational function. Degree of the numerator is greater than the degree of the denominator. The result is that there is no horizontal asymptote. And f of x simply approaches either plus or minus infinity as x approaches plus or minus infinity. Okay, so one more case, a special case. There's always got to be a special case, right? So in this case, the numerator degree is still greater than the denominator degree. That was case 3 that we just looked at. But in this case, in particular, the degree of the numerator is 1 more than the degree of the denominator. Exactly 1 more. Okay. So if we look at this function and if we look at the ratio of the leading terms, we can see that n is equal to 2 and m, the degree of the denominator, is equal to 1. Okay. And if we look at the graph to inspect the end behavior, we can see that as x gets very large, that the function value is increasing without bound. As x gets very negative, that the function value is decreasing without bound. Okay, so in other words, the end behavior, just kind of shorthand notation, f of x is approaching plus or minus infinity as x is approaching plus or minus infinity. Okay. So it is still unbounded behavior, but this time it's a little different because the graph has what is called an oblique asymptote. Okay, oblique. P. Remember how to spell that. Okay. And I'll try to sketch it in. It won't be great. I'll pull Desmos over in a second and replot this for you so you can see it. The oblique asymptote, this is terrible, wait until I pull Desmos over, is a line. Okay, it's like this slanted line. So an oblique asymptote will always be a line, not vertical, not horizontal, but a slanted line. And the function will ultimately approach that line as x approaches plus or minus infinity. Okay. We can find the equation of the oblique asymptote as follows. All right, I'm going to erase this stuff so I can scooch down a little. So remember that our rational function is n of x divided by d of x, and if we were actually to divide those out, we would end up with the quotient function q of x, and then plus some remainder r of x over the divisor, the denominator, d of x. Okay. So what we actually need to do to find the equation of the oblique asymptote, q of x, is to go ahead and do that division using either synthetic or long division. Now in this case, because our denominator is an x plus 2, and remember that's the same as x minus minus 2, we can actually use synthetic division on this one. So let's go ahead and do that because it's a little easier. So in the numerator I have 3x squared plus 0x minus 1. And then in the denominator we have x plus 2, which again is the same as x minus minus 2. So based on the definition of synthetic division, I'm going to put a minus 2 here. I just totally screwed that up. Hold up. I got to erase this. Obviously, that's not where I meant to put my box. I meant to put my box here. And my minus 2 here. Sorry about that. Okay, bring down the leading term, which is 3. Negative 2 times 3 is negative 6 plus 0 is negative 6. Negative 2 times negative 6 is positive 12 minus 1 is 11. All right. So remember how synthetic works. This is the remainder. I don't know why I just made a B. I meant to make an R. And this is q of x, our quotient. This is going to be 1 degree less than what we started with. We started with an x squared, so this is going to be an x. So in other words, 3x minus 6. Okay. So that is my quotient. Okay. And your Q of x is always going to be in the form of a line y equals mx plus b. And that's what we just found, that f of x is going to approach q of x, the line mx plus b, as x approaches plus or minus infinity. Okay. Sorry, I'm just trying to, yeah, plus or minus infinity. Okay. So it is still unbounded. It's still going to plus or minus infinity as x goes to plus or minus infinity. But specifically, it is going to approach this line. Okay. Now, like I said, let me pull Desmos over and I will plot this for you so you can see it. All right, let me just reload this whole thing. I always just like to reload it every time I start something new. All right, so our function was 3x squared minus 1 divided by x plus 2. All right, and it looks like we need to just zoom out a little bit. Yeah, so I can see the whole thing. And now let me go ahead and add in the line of that oblique asymptote, which was 3x minus 6. All right, and now you can see, let me just change that to a dashed line just because it's kind of fun. You can see, definitely that the function is approaching that line as x gets very large or as x gets very small. Okay, so finally on the next page, let's just do a brief summary of all the cases we just went through for horizontal asymptotes. So again, we have a rational function in lowest terms. There's no common factors. Okay. And again, the main thing we want to be looking at is the ratio of the leading terms. Okay, and remember that n is the degree of the numerator and m is the degree of the denominator. If n is less than m, then the horizontal asymptote is going to be the line y equals 0. In other words, the x-axis. If the degrees are the same, then the horizontal asymptote is going to be the line y equals a sub n over b sub m. Okay, where those are just the leading coefficients. If n is greater than m, then there is no horizontal asymptote. Okay, the function behavior is just unbounded on both sides. The special case we just looked at, if the degree of the numerator is exactly 1 greater than the degree of the denominator, then there's still no horizontal asymptote. Okay, but what we do have is an oblique asymptote. I'm not going to write that out again. It's oblique. Okay, so there is an oblique asymptote equal to q of x, the quotient of the numerator over the denominator. And again, that is a line, okay? Y equals mx plus b. But still, the behavior is unbounded. All right, so before we go on to the graphing, let me just go to the next page real quick. Kind of learning, using everything we've just learned, to just analyze the rational function. So in other words, I've given you a graph here of a rational function. It's got a vertical asymptote indicated, it's got a horizontal asymptote indicated, and all you need to do is fill in the blanks here. All right, so what I want you to do is pause briefly, fill in the blanks, and then I'll resume and you can check your answers. Okay, so number one, as x approaches 1 from the positive side, so of course 1 is the vertical asymptote here, so we're saying as x is approaching from the positive side, what is the function value doing? It is approaching infinity. Okay. As x approaches 1 from the negative side, so this time we're coming in this way, what is the function value doing? It is going to negative infinity. As x approaches infinity, so in other words, as x is getting very large, what is the function value doing? Well, it's approaching the horizontal asymptote, which is at 2. So f of x is approaching 2. Also, as x approaches negative infinity, the function value is also approaching the horizontal asymptote, so f of x is going to 2. Okay, the domain of the function is obviously any number other than x equals 1. So, paren negative infinity comma 1 paren union with paren 1 comma infinity. The equation of the vertical asymptote is the line x equals 1. The equation of the horizontal asymptote is the line y equals 2. So when you write the equations of the asymptotes, make sure you include the x or the y, just to be clear. All right, so it's time to pull everything together now. We've learned how to analyze the functions. Now we want to take all that information and use it to graph a rational function. Okay, so given some rational function, we're going to go through all the following steps, as applicable. You don't need to do all these steps to graph every function. All right, so the first thing you want to do, start by factoring the numerator and denominator, if possible. You want to find the domain of the function, and obviously you need to exclude any values from the domain that would make the denominator equal to 0. In one special case, if there are any common factors in the numerator and denominator, go ahead and cancel those to put the function into lowest terms. However, if you do cancel a factor, remember that there will now be a hole in the graph, and remember that is called a removable discontinuity. Okay, so you have to remember to go back and put that hole in the graph, that open point. Okay, step 4, solve for and plot the x-intercepts of the graph, if there are any. To do that, take the numerator and set it equal to 0. Okay, because remember, those are the points that will make the function value, f of x, equal to 0. Those are the zeros of the graph. So you set the numerator equal to 0, solve for x. The solutions are the x-intercepts of the graph, if any. So those will be the point or points x, 0. Number 5, solve for and plot the y-intercept, if there is one. Okay, and remember, to do this, just evaluate the function at a value of x equal to 0. Okay, so this will give you the y-intercept, if there is one, the point 0, comma, y. And the reason we include this step is it gives us another point, and it's very easy to evaluate f of 0. Solve for and sketch in the vertical asymptotes, if there are any. So remember here, set the denominator equal to 0. Solve for x. Which values of x make that denominator equal to 0? The solutions are the vertical asymptotes, the values that x can never take on. And in general, this will be the same as the values that you excluded from the domain up in step number 2, unless you happen to have a special case of a common factor. And number 7, solve for and draw the horizontal or the oblique asymptote, if there are any. And again, we just finished going through this. Compare the degree of the numerator to the degree of the denominator, and basically use that summary table we just completed to determine what your asymptote is going to be. All right, if you want, you can test the function for symmetry. This isn't necessary, but it may help you draw the graph. If f of the opposite of x is equal to f of x, that means it is symmetric with respect to the y-axis. And if f of the opposite of x is equal to the opposite of f of x, then the graph will be symmetric with respect to the origin. Okay. Also, if you want, again, not absolutely necessary, but you can make a sign chart to analyze the sign of the function between the zeros. And then you can just kind of use this as a guide in plotting. This is kind of like what we did back in chapter 2 for polynomial inequalities or rational inequalities. Basically draw like an X number line, mark any of your zeros on the X number line, which then separates the axis into various intervals, and then just pick a test number in each interval, calculate the sign of the function in each interval. Like, is it positive? Is it negative? Is it positive? And I'll just give you a little bit more information about what the function is doing in each interval. And again, all function values, y values, in that interval will have the same sign. They'll all be positive, or they will all be negative. Okay. And then, if needed, if you're still not certain what the function is going to look like, then you can just calculate some additional points. Just a little bit of point-by-point plotting. You can pick values of x and then calculate the corresponding values of y. Okay. And in general, just use your knowledge of what is going to happen as x approaches a vertical asymptote. Use your knowledge of what the function is going to do as x gets very large or very negative. Okay. And then when you think you have enough information, basically just finish off the plot by drawing smooth lines, adding arrows. All right, so let's go through an example on the next page, and then on the following page is a grid where you can plot the function. Sorry, making sure this is going to work. All right, so we've got x squared plus x minus 12 over x squared minus 4. First step is to factor the whole thing, numerator and denominator. So let's see, the numerator would factor as x plus 4 times x minus 3. And then the denominator, of course, factors as x plus 2, x minus 2. X minus 2. Okay. So from that, then, we can find the domain. Obviously, we cannot let x equal -2 or +2. So I'll just write shorthand notation, x cannot equal plus or minus 2. All right, special case, cancel any common factors. There are none, so we don't have to worry about that step here. Solve for and plot the x-intercepts. So again, we want to take the numerator and set it equal to 0. Because when the numerator equals 0, that's when y will equal 0. So in this case, I'm taking my numerator, which is x plus 4 times x minus 3. I'm setting that equal to 0. Okay, that will obviously occur at x equals -4 and x equals +3. So that gives me 2 points, and we can go ahead and add those to the plot. So the first point would be the point -4, 0. Go ahead and you can put that on your plot. And the second point would be 3, 0. So that's like right here. Okay, solve for and plot the y-intercept. So in other words, I just want to plug in x equals 0 into the function. Okay, so you can use the factored form or you can use the original form. In this case, it looks just as easy to use the original form, because if I do 0 squared plus 0 minus 12, all right, again, I'm just substituting in x equals 0, and then divided by 0 squared minus 4. So I'm going to end up with -12 divided by -4, which is +3. Okay. So this gives me my y-intercept, the point 0, 3. All right, so we can go ahead and add that to the plot right here. Oops, missed it a little. I'll just make it really big. Solve for and draw the vertical asymptotes. Okay, so again, this is where the denominator is equal to 0. Okay. And in this case, we basically already solved for that up here because there was no special case. So in other words, the vertical asymptotes are going to be the lines x equals -2 and 2. All right, we can go ahead and add those to the plot. So you're going to have a vertical line at x equals -2 and a vertical line at x equals +2. All right, solve for and draw the horizontal or oblique asymptote, if any. All right, so again, we want to compare the leading terms. So notice that the degrees are the same. N is 1, M is 1. So in that case, we're going to look at the ratio of the leading terms, both of which are 1. So therefore, 1 over 1 will give us a horizontal asymptote of y equals 1. Okay, so we can go ahead and add that to the graph. All right, so y equals 1 is right about there. like that. All right, test for symmetry. Yeah, you know, we can go ahead and do this if we want. Let's see, if f of negative x, so for example, if I were to do f of negative x, so in other words, in my original function, everywhere instead of x I plug in negative x. I won't go through the whole thing, but we're basically going to end up with x squared minus x minus 12 over x squared minus 4. Okay, that is not the same as f of x because of the sign change right here. Okay, so in other words, there is no symmetry with respect to the x-axis. And then if f of negative x is equal to the opposite of f of x, which just at a glance you can see clearly it's not. Okay, so there is also no symmetry with respect to the origin. All right. Okay, so no symmetry, that doesn't really help us much. Construct a sign chart. Okay, let me scooch this down a little and then just do a little erasing here. Okay. So just to analyze the sign of f of x between the zeros. Okay. So the zeros are at -4. Then we have an asymptote at -2. Then we have another asymptote at +2. Then we have another 0 at 3. So that basically splits the number line up into 1, 2, 3, 4, 5 different intervals. Okay. And if we were to pick numbers, like for example, here I might pick -5. And then I would just punch in to the original function. If I put in x equal to -5, what do I get? Well, it turns out I get the point -5, and then I'll just approximate it in decimal form. It's about 0.4. Okay, so in other words, it's positive. So everywhere over here to the left of -4, the function is going to be positive. Okay. In between here, in between -4 and -2, the obvious choice is to pick a test number of -3. So if I plug in x equals -3, I get out a y value of about -1.2. So that means everywhere in that interval it's going to be negative. Here in between -2 and 2, the obvious choice is 0, and we actually already know that f of 0 is 3. Okay. In between 2 and 3, there's no convenient number, but you could pick an x value of 2.5. And again, just plug that into the function. If you put in x equals 2.5, you should get about, that's supposed to be an approximately sign, -1.4. And then in our last interval, just pick x equals 4. And if you do that, you should get f of 4 is about 0.7. Okay. So to just kind of summarize the signs there, in this interval, it's positive. In this interval, it's negative. Here it is positive. Here it is negative. Here it is positive. Okay. And then calculate any additional points if needed. Well, I don't know. Let's add all these points that we just calculated, and then we'll see if we need some more. So in other words, we had -5, 0.4. So that's going to be what? About here-ish. We had -3, so that's here. -1.2, so that's about here. Okay. We had 0.3, we already had that one on the graph. We had 2.5, which is here, -1.4, so that's going to be, what, about here? And then we had 4, 0.7, which is what, about here-ish? Okay. Now, the question is, well, do we need any more points? Okay. We know over over in this region, above 3, it's going to be positive. It's also going to approach that horizontal asymptote. So in other words, I have a pretty strong hunch that this is going to go like this on this side. Okay. In between 2 and 3, if you go back to our sign chart, it's going to be negative. Also, as the function, as x gets closer to that vertical asymptote, it's going to obviously shoot down to -infinity. Kind of like that. Okay. And once we've kind of talked about that side, maybe you can come to the other side and see, oh yeah, it's going to do about the same thing. This is going to shoot down, you know, approaching that asymptote, and this is going to approach that horizontal asymptote. Okay. Now the only question is, what's happening in this middle part? We only have the 1 point. Again, if you come back to the sign chart, between -2 and 2, we know it's going to be positive. So there's really only one thing it can kind of generally do, which is going to be something kind of like this and this. All right. I mean, if you're not sure, you could plug in -1 and 1 and calculate points if you want. It's not strictly necessary if you have a good feeling that you know what the function is going to do. So in general, that's what it's going to look like. And then, as always, we can kind of check it by using Desmos. So let me pull that over. I'm going to erase everything. And again, I'm going to reload this. And then I'm just going to type in the function we started with, which was x² plus x minus 12 divided by x² minus 4. Okay. Looks basically like what we just made. We can add in our vertical asymptotes. X equals -2, x equals 2. We could even add in our y asymptote. What was it again? Y equals 1. Okay. Zoom out a little, and yeah, you can see right away that it definitely approaches that asymptote and the vertical asymptote, so everything looks good. All right, so what I've got then on the last 4 pages are 2 problems for you guys to try. So here's one, problem number 1. There's a grid. Problem number 2. there's a grid. Okay, so I want you to go ahead and work through those, kind of using the steps, just to get a little bit of practice. And then, of course, you can check your plot on Desmos once you're done. Okay, and the last thing I want to comment before I end is actually I just noticed on this problem number 1 on page 69, I want you to replace that one with a different problem. I want you to do this. F of x equals 2x plus 4 over x minus 1. Okay, so again, just jot that down. Go ahead and replace the problem with that. Make sure you make that same replacement on the next page. Okay, so again, just cross this one off, do this one instead, 2x plus 4 over x minus 1. And problem number 2, I'll just make one comment, which is to notice that the degree of the numerator is exactly 1 more than the degree of the denominator. Okay, so that should give you a hint as far as the end behavior of the function. All right,